Welcome to lecture number 2 of module 5, that is load dispatch center functions. In the previous lectures I explained about contingency selections, restorative and emergency control actions. In the contingency selection, that is a part of contingency analysis, I was discussing that we can go for the formulation of performance indices. Those are useful for categorizing the critical contingencies in the system. So, in the previous lecture, I discussed about the real power flow performance index. Now, here I will discuss your voltage, or you can say reactive power performance index, and which can be defined as follows. This PI, which is I have written the PIV, means it is for the voltage performance index, and basically that is used for your MVR security or voltage security analysis. Here again, this function is similar to your real power flow performance index, and that if you can see, I just defined here the PI for that, and if you can say it is a real power flow, that is equal to summation of here I is equal to 1 to here all the number of lines. Here it was your omega m over your 2n, and here I was writing this PLM over PLM maximum value, and then it was power 2m. Here basically it was m. So this function is almost similar to this function. You can see this is the power flow performance index, that is it is a real power flow PI. Why it is real power flow? Because we are taking this here variable the PLM, that is a power flow PL in particular line m, divided by the rating of that line, that is a PLM maximum value, and then we are going for the 2n, that is n is your exponent. Here omega m is giving the relative importance, as I explained yesterday in the previous lecture. Here that is the divided by 2m, it is giving relative importance of that particular line. Normally this value is kept 1, so we are giving the relative importance for all the lines outages equally. Similarly, here in this voltage performance index, here instead of the voltage at the particular bus, we are just taking the difference between the specified. The question here, the PLM, always we go for this equality. The PLM of any particular line should be less than or equal to this PLM of that line to this maximum value. So it should be always less than or equal to this value. So this side limit is again if you are taking mod, so it will be 0 value, so there is no problem. But the voltage, if you will see the VI here, it should be lie between the two limits. Here I can say VI maximum value, and then here it is VI your minimum value. Means your the voltage on any particular bus should lie between the two limits. One is your its maximum value and another is your minimum value. So we have to now go for this difference. How much this where you are operating, what is your voltage? If it is only one value and there is no lower side value, then we can go for the similar expression. But here, since this VI should lie between these two ranges, so we are talking about the difference. Now the V specify, what should the V specification of any bus? We want that suppose your bus voltage is 1.05 is the upper limit and the lower limit is 9.5. We want our specified voltage here should be your I, that is specified. It is the sum of these two divided by 2. Means it is the average of these two. So VI is specified, it is equal to your 1 per unit. So here this V specified is the, even though sometimes it is a general value I am talking, even though if you are not going for 1 per unit or something else value, then you can specify how much you want and how much it is a deviation. We want that your voltage should operate here at the specified value, so this will be 0 and this will not go in the PI addition, because it is addition for all the buses. So if all the bus voltages are equal to its specified voltage, then this value will be 0. Otherwise, if there is some deviation, the voltage will be, this PI value will be higher, and that gives the relative severity of this. If this PIV is larger, means I can say for that contingency our system is most critical, and so on and so forth. Now again here this we are putting the word that is omega VI. It is also giving the relative importance of a particular bus. in this PI contribution. Why it is so? Because we know even though some buses, even though violation can go even the more than that its limit, it can cross, but that may not be so critical. But some buses, even though small deviation in that voltage is very, very critical. So we can put some value more other than unity here, means that will give the relative importance of that value. 2n is divided here to normalize this almost, so that we should not keep on increasing the value. Another value here to make it, what is the range of the limiting value? Here we were using this, again here was also range. Range means it was a P max minus 0, because from 0 to P max it can go, of course in any direction. So here this value was P max, here we are taking the Vi limit, and this Vi limit is defined as your here the Vi max means the maximum value at ith bus minus minimum value at ith bus divided by 2. So this value is kept here, and then we can go for summation for all the buses. Here again NB, here it was number of lines. Because we are talking the line flows, so number of lines we are considering. Here we are talking about the bus voltages, so number of buses are keep on going to be added. So that's why here I have written the NB is the total number of buses in the system. Similarly, some people say that the voltage performance index may not be adequate. Then they define another, right, a reactive power performance index similar to your real power flow performance index. Basically, this reactive power performance index is reactive power generation, means how much reactive power you are putting into the system, how much requirement is there, and that gives your relative criticality of the system. Similar to PIV, here we are adding number of NQ, means how much sources you are having in your system, means how much reactive power. Again, just I want to give you one example. In your power system, there may be number of NG number of generators, means real power generators, and there may be your NQ reactive power generators. Now this NQ is always greater than or equal to NG. Why this is so? For example, some of the generators, your real power generators or your alternators, so they are generating the real power, and they can also generate the reactive power. So this NG is also reactive as well as real power generation. But in NQ, it is not necessary all these reactive power generators will generate the real power. That is, the reverse is not true. Why? Because let's suppose you are having a static condensers, you are having FACS devices, you are having simple capacitors. They can generate reactive power, but they cannot generate the real power. So this NQ, just we are considering are the reactive power sources, including your real power generators and synchronous condensers, your FACS controllers, as well as the other capacitors or reactors in the system. So always this NQ is more than your NG. This is real power generator, this is a reactive power generator. So here we are adding the reactive power generated for all this NQ in the number. So I have written this NQ is the total number of reactive power sources in the system. Now let us come to this point again. Here this WQI, it also shows the relative importance of particular reactive power source. The difference here, what is the reactive power generation of that ith, just we are adding here. So the QG is a reactive power generation at I means ith bus minus QGI specified. This QGI is specified how much you can generate. This basically defined at the QGI specified here with this expression that QGI max plus QGI min divided by 2 is the specified. Means we have the some limit and then we are going to generate in that. You can also see already we discussed about the reactive power capability of an alternator. If you remember what I did, this is a P and Q curve just I have drawn, and we found this is your field heating limit, this is your armature heating limit, and this is your end heating limit. So this was your reactive power capability limit. So this was your positive Q, it was your negative Q. So this was your Q min and this was your Q max that you can generate. So this is the average of this we can go for here. But some of the devices, for a capacitor, it will generate because it has no limit. It depends upon the voltage. How much capacitor? So its value here is V square into omega C. It will be the reactive power generated by a capacitor simple. But if you are having static var compensators, SVC also I have explained. In SVC, it is a plus minus certain value. You can say, let's suppose 100 MVAR. So it can go for both sides. So normally we want that this static var compensator should neither generate neither should absorb. So this is basically the specified value for this will be 0, Q specified. For this Q specified, we can take average of this, so it may be this some positive value. So these are the basically the limits that we have to see and what is the specified. Now question, why we want this specified value is 0? If you are putting a huge expense for putting a SPC in your system, it is very expensive device of course, then we want to operate this, because then we will have the more margin because these systems, these are used not for simply providing the reactive power support, because the reactive power support can be provided by your capacitors and reactors. But if we have a more margin here, then during the emergencies we can control this very effectively, and we can provide much more effective control to normalize the system. So that's why we want here that it should, in the steady state, it should not generate. For example, we have one SBC in the Kanpur here, that is a power grid substation. Mostly it is operating in the capacitive mode. It is generating reactive power every time because it's our system demands. But we want that it should generate very less amount of reactive power or absorb, otherwise we will have a less margin. For example, this SBC which we have in our UP. Let's suppose it is already generating, actually basically its rating is plus minus 280 MVAR. Let's suppose it is generating 280 MVAR in the steady state condition. If the faults come, there will be no margin. So it will already it is hitting the limit, and it has no control during the emergency, because these devices basically are used for the emergency control. So that's why this is the specified. We are adding the maximum to the minimum value, and we are taking the average between these two limits. Similarly, another is your here, that is your change in your reactive power limits, that we are dividing. This value we are just making it significant amount, because if you are you can see how much margin you are having, what is your range here. If you are having less range, then this value will be more. Means you are just operating how much closer to this limiting value. So this limit is basically giving idea. For example, the two systems, you can see one is here, the limit is, let's suppose 1 plus 1 to 1 you are having. Another reactive power generator you are having 2 to minus 2. Now you can see here in this range you are having this value is 4. Here you are having 2. So if you are dividing by 2 with the sum here value, means this value is very close to that. For example, let's suppose this is operating at here 0.5, and this is also operating at the 0.5. The specified value for these will be 0, because specified is, if you are adding plus and minus here negative, so it will be 0. So what we can get here, 0.5 divided QG, it is generating, this is your QG, 0.5 divided by 2 for this case, and for here it is your 0.5 divided by 4, means you are here operating 0.1125, here you are generating 0.25. So this value we can say it is very critical. Why? Because you can see the range we are having 0.5 only margin to its limit, but here 0.5 we have a more margin. So this case is less critical than this case. So this gives basically the relative, that's margin how much you are having. So this is very important factor. If you are not using, then you cannot say then both will be equal here. So it's showing that the Q limit is divided to take the importance of that range also, and that range is defined by the change in the QGI limit is equal to your QGI max minus QGI min divided by 2. Just we are taking average here. Now let us go for some methods for the contingency selection. In the contingency selection, first and very simple method is your DC load flow method. This DC load flow method is basically used, as I said, it is only for the real power flow security analysis. because, and it is DC here, it is not direct current. You should not confuse it. This is no doubt is a load flow solution. It is called DC because we are ignoring the voltage term, only we are taking the delta. I'll just show you. The assumptions behind this program, this method, is the line resistances and all the shunts are neglected. You can see here, first one. Transformer taps are ignored, means we have to set at a unity, this nominal value. The voltage magnitude at all the buses are assumed to be unity. While formulation, we put it 0, 1, and then we go for calculation. The voltage here, angular difference between the two buses is very small. With these assumptions, we can write the power flow equation here in this fashion. You remember this expression very well, that is a P at flow in the line is V1, V2 upon X12 in that line, sine delta 1 minus delta 2. This is basically power flow between 1 to 2 bus. Now using this, and this expression is only valid when R is 0. So already we have taken in this expression, otherwise there will be some last term will be also appearing. It is said the taps already we have set unity, voltage magnitude is 1, means V1, V2 is unity, so we are getting P12 divided by X12. Here we are saying the angle is very small, means the delta 1 minus delta 2 is also very small. Already the angles are small, delta 1 and delta 2. And once two smaller quantities are going to be subtracted, it becomes further smaller. So here, and then if we sine theta, now we can write as the theta for the smaller value. So this is nothing but your delta 1 minus delta, means we can, in the radian we can write this. So this expression here you can see just I have written, where X12, now it is a general way it is written, that for any line which is connected between bus I and J, we can write the Pij in that line, that is equal to 1 over Xij multiplied by delta I minus delta J. So this shows the power flow from I to J. So it is just delta I minus delta J, we can write this, where the delta I and J are the voltage angles at the bus I and J respectively, as I told you. Now, the DC load flow solves the following equation to compute the angle vector this for the value of the real power flow injection. Now, we can use another expression, if you can remember. That expression here, we were using this expression, that is the delta in terms of power injection. Means here in this one, we cannot directly write this. Here we can, if you write here the general PL, I can say we can write one matrix here, and then we can write it the delta matrix here, delta vector, sorry. And this matrix may be yours somewhere, it I can say, this is some matrix we are here representing, let's suppose a matrix. This matrix is not a square matrix, so that you cannot get the delta. If you can get delta, here in the DC load flow, what we do, we obtain the deltas. And once you can get the delta, you can calculate the line flows. And that is required in the real power security analysis, because we require the line flows. If the some line is out, what will be the power flow? So we require the deltas here from this expression. Here, this matrix is your this M cross N. N is the number of buses and M is number of line. Here all this delta 1 for the slack is always assumed to be 0. So here I can say my N minus 1 matrix. So M is number of lines in the system, that is always more than number of buses, are equal to that. And here N minus 1, so order here it is not square, so you cannot invert it. So you cannot get the delta. Now we can use some other expressions for calculating this. So here from this expression, you know the injection at any bus I, that we can write the summation of this Pij, and this is the all the lines that are connected with this bus I. For example, if you are, this is a bus I, here if you are having several lines here, so what will happen, this is your J, it may be your K, it may be your L. So it is a summation of all the lines, that is here Pij, Pik, Plk, and then we can add together. So here this from this expression I can write this Pi at individual bus, it is the summation of all the power flow, that is 1 upon your xij, and here delta I minus delta j. Here you basically we are going to delta 1 to all this the connected line, means your j, k, what are the buses that it is, but it is not I, and then we are keep on adding. So what we can do from this, we can form a matrix that is your p vector, that is a injection at every bus in the system, that can be formed like a matrix here, and here we can write the delta vector here. So that matrix here is known as your Bx matrix. This Bs matrix, again we'll take one example, then that will be more clear to you. In that this Bx is the diagonal and off diagonal terms that can be defined. In this Bx, that is a diagonal term, here I can say the Bxii will be your summation of all these elements here that are connected at the bus I. So here I can go for the Bxij, it is nothing but negative of your xij, means the element between I and j, off diagonal here I am talking. You know the diagonal terms are, these are the diagonal terms, and off diagonal terms are there. Then we are with the negative sign xij. Why that negative sign is coming? Because the negative with the j here, negative with the k will be coming, and then it will be there. We will just solve one example, then it will be more clear. So what we can do, this we can have this matrix. Now we can exclude the slack bus. So delta at that bus is assumed to be 0. So P also we can ignore because the losses etc. is met by slack bus. So this matrix is nothing but your n minus 1 cross n minus 1, and that is a square matrix. It is a non-circular matrix as well. So we can invert this, so we can get the delta here. So delta can be calculated by the power injections. We know the loads at each buses. We can form this XV very clearly during the outage and other things, and then we can calculate the delta, and that delta is used here, then we can calculate the power flow. So this is basically the solution of this. It is non-iterative, and hence it is quite fast. To see this example first, I will discuss that example. Let us see here. This is a 3-bus example that we are using the DC power flow, and this reference is taken from the Power Generation, Operation and Control by Wood and Woolenberg book. Now we are having here your 3-bus system, and in this case just we are assuming the bus 3 is your slack bus, means here angle is 0, and the lines 1, 2, 1, 3 and 2, 3 are connected. The impedance of the line, that is we are only ignoring the resistance as per assumptions of DC load flow. Here X23 is 0.25 per unit on 100 MVA base. Here we are taking the MVA base is 100. Now here also we have the X. So 1 upon X2 it is a 5, X2 is 0.2 here. So 1 upon this means this is equal to 1 upon 0.2, we are getting this. Here it is a 3.2, you can 3.2 is 0.25, so it is 1 upon 0.25, and here 0.25 means 0.4, so 1 upon 0.4 we are getting these values. Now we have to form the matrix B first, that is Bx matrix we are going to form. Now this Bx matrix will be your 2 cross 2 matrix. Why? Because this is your 3-bus system. So n minus 1 cross n minus 1 matrix order will be there. So this it will be your 2 cross 2, means 3 minus 1 is 2. So 2 cross 2, sorry, it is 2 cross 2 matrix will be there. Now these are the your here and here, they are the diagonal elements, and as I said the diagonal elements are calculated, that is a summation of, let's suppose I am talking about the bus 1 here. At bus 1 it is the summation of all the lines that are going from that one. So 1 over x means here this I can say B11 will be your 1 over x12 plus your 1 over 1 x13, means admittances, the sum of the admittances, that is the line which are connected at bus 1. So here 1 upon 0.2, 1 upon 0.4, so how much this? Means this will be added 1, 2 and this will be added, so it will be your 7.5. Now this off diagonal of this first element, means we are talking 1, 1. Now I am going for, this is your 1, 2, here 1, 2. So this is your 1, 1. 1, 2 is, as I said, it is the negative of, first write negative, of the admittance between 1 and 2. 1 and 2 admittance is 5, because here 1 upon x2 is 5. So it is a 5 matrix. Similarly, here 2 and 3 we are talking. Basically, here we are talking 3 is your select. So we are taking the value between 1 and 2 again here. So it will be similar to with the negative 0.5. 1 and 2 here means 2, 1. This is your 2. So 2, 1 we are calculating. Of course, one way you can check this matrix is symmetrical. So this is a 5. So this is a 5 it will be. Now here the value we are going to calculate, that is a diagonal element, and that diagonal element is nothing but, here it is the summation of admittances of those lines, those are connected at bus 2. So here 1 upon 0.2 means here 1 upon 0.2 plus 1 upon 0.25. So this will be equal to your 4 and here 4 and 5, it will be your 9. So this is your Bx matrix. So it is very easy to form. Without any doubt, you can create even though your lateral system is there. So suppose your several lines are there, so keep on going for this one. So you have to see this your diagonal element of any for bus 1, then it will be the sum of all the admittances of the line connected at bus 1. For 2, it is the sum of the admittances of the line connected at the 2. Now this off diagonal elements, if you are talking about 1 and 2, then you have to take the admittances, negative of the admittances between bus 1 and 2. That's I have written here, and similarly you can keep on going to form this. So this is your Bx matrix, which I have written also here, you can say this. Now you have to invert this. As I said, this relation is showing your P is equal to Bx delta, but we want delta so that we can have the Vx inverse and then we can multiply P vector. So the inverse if you are going to take, then you can very easily you can take the inverse. Here you can take this, change this one, change the sign here, and then divided by determinant of this value, you can get this. And it's very easy to cross 2 matrix inverse. So this will be the inverse. Now we have to calculate the P vector. P vector is nothing but the power injection at 1 and the power injection at 2. And again, you must always be very careful, it is in per unit, because admittances we have taken in the per unit, so the real power flow also we have to take in the per unit. Also you have to be very careful, if the power at any bus is here injected, then this value is the positive. If you are taking the bus power at that one, then it is taken as negative. Means the load are treated as a negative injection, and generation, of course, they are injecting power into the system. Those are taken as your positive injection. Now in this figure, here you can see, at bus 1 it is a 65 megawatt is injected. So 65 divided by 100, because we have to convert in the per unit. This is the power divided by base. So 0.65 here, 0.65 will be your value for 1. So it is 0.65. Now for this one, for the 2, it is a load, and this load is 100. So 100 divided by 100 is 1, and since it is a load, so it is a negative value we have to take, and then it will be your minus 1.0. So using this Bx inverse, use the P, means I have just written here for calculating the delta 1 and 2, because delta 3 is 0, already we have assumed it is just like bus. This is the Bx inverse xb. Here we are putting the P that I have taken here, you can see very easily, and then you can multiply it, and after multiplication you will get the delta 1 is your 0.02 and delta 2 is minus 0.1 radian. So these angles are in radian we are getting always, it is not in degree. So normally people get confused in the conversion of the per unit quantities, treating these P values. If you are taking actual value, then everything is wrong. So this is in per unit, this matrix is on the per unit impedances of the line, this is in radian, so we are getting already radian here. Now we can calculate with help of lambda 1, delta 1 and delta 2, we can calculate the P12. Now the P12 that we can define, as I said here, this P12 is nothing but 1 over x12, here delta 1 minus delta 2. So we can 1 upon x2, it is nothing but your 5, already we have calculated the 5. Delta 1 is your 0.02 minus 1 0.1, so it is a plus 0.1, and then you are going to get here 0.6 per unit, means it is your 60 megawatt. Now similarly you can calculate your P32. This P32 is, you can say again 1 upon x32, here delta 3 minus delta 2. So this is the direction which is flowing from 1 to 2. So this value is 60 megawatt, that is flowing from 1 to 2. In this diagram, what is this? So this is 1, 2, it is your 60 megawatt flowing from 1 to 2. If you are going to here, already we have marked the sign. So 3, 2 just we are calculating here. If it is a negative value is coming, means the reverse direction is reverse. So here we can calculate P32 by putting these value 3, here delta 3 is 0, already we have assumed because it is a slack bus. So 1 upon here x32 is 4, 1 upon this, you can see here value I have written, and then I can just put here 4 into minus delta 2, and here it is a minus it is plus, and then we are getting 0.4, means it is your 40 megawatt. Similarly we can calculate the 1, 3, and we will get point here, you will get 0.05 per unit, or it is your 5 megawatt. So now you can see here in this direction is 65, here is a 60 is flowing here, 5 is flowing here, and the 60 is going, and this value is going to be 40 here. So this 65 is just divided into 60 in this line 1 to 2, 5 is coming from 1 to 3, and this here 40 is going, means this generator is generating how much? Is 35. Why? Because 5 is coming here, so the remaining 35 is met by the slack bus generation, and then this is the generation of this megawatt of this one. So this is the application of, you can say it is a non-iterative DC load flow. We can calculate the power flow very easily by simply solving one iteration. You can say here what we are doing, we are taking only one iteration for one contingency. However, if you are going for the load flow, so every time you have to, there's if 4 iteration or 5 iteration quantities are there, then you have to iterate accordingly. So this is we can calculate, and this is one way that we can obtain this line power flows, and again we can. Another I want to mention here in this power flow definition, that's I use here PI for line flow I am talking. It is a summation of, here I said omega m upon 2n, here the PLM upon PLM maximum. You can use here the PLM and PLM max value in the per unit or in megawatt, but the proper care should be taken that if you are taking the line power flow in the actual value, that is a megawatt or kilowatt, then you have to use this rating also in the same unit. So if there will be no change. If you are using per unit, you can use both in per unit, and then you can solve it without any problem. So you can see how fast, and it is called DC because we have ignored the voltage. We are only taking this here deltas, and this deltas giving directly power flow. Although these power flows are not so accurate because we have ignored the losses, we have ignored the voltage, but for your rough ranking, that is even though giving very good result for the real power flow security. Another method just I am going to discuss you is the network sensitivity or the distribution factor methods. Means here the distribution factor methods are very popularly used for the contingency selection. In this, the basic principle, basic motive behind this, the generation shift, we are having the different factors. The factors corresponding to the generator outage, so it is called generation shift factors, and the factors corresponding to your line outages, then it is called the line outage distribution factors, and then those factors are stored, those are calculated at the base case. What is the base case? Means actual operating system without any outage. So we can calculate at the base case loading, and then we can use the same factors for the different loading. Again, that loading should not be very high. If its loading is very high, that factors may give wrong or inaccurate results. So first let us consider the outage of a generation, means outage of a generator I having a pre-outage, means it was generating the PGI naught value, means it was giving power to that, and then it was outage. After this outage, then we want to see what is the change in loading of your transmission line. Earlier the power flow, we are knowing that the line that's in the power flow in all the lines, it was nothing but your this power flow, I can say F now here I have defined. So this was your naught value when it was generating this. Once this generator was out, we are keeping the load constant. What will happen? That outage generator will supply power, means this power will be supplied by other generator. Normally let us take is a slack bus power generation. So there will be rerouting of the power flow in the transmission line. To see this, what will happen, just I will explain you. If we will take this example here, even though for this system, let's suppose this generator is outage. This generator is tripped. What will happen? If the load is, this is a constant, so this generator will be, instead of this, it will be generating 100 megawatt. And if it is generating 100 megawatt, the power in this will be rerouted. Power will be totally different. Here the power will be, maybe the power just we can calculate, I am not sure how much value, but this 100 will be shared, one will be flowing like this, another will be flowing like this, and then it will be 100 megawatt. So since it is having more impedance compared to this, here you can say 0.6, here 0.5, so the most of the power will be flowing here compared to this. So normally here it will be 60, here it will be 40 megawatt will be flowing. So this is what happened. Now the power is rerouted, power is the different. So here the same way just I am explaining that once this was the, earlier it was generating, after outage of this, there will be rerouting of the power flows in the lines, and then we can see how much change from the previous one. So the factors are defined by, for line L, line means for any particular line, because we are having m number in the line. So this factor is AL, I is corresponding to outage of your IS generator, is defined as the change in the power flow in the LF line divided by the change in power at IS generation. In this case, what is happening? Change is your negative of this. Earlier it was injection, final value is 0. So what we can say, final, this delta Pi is your PGI final minus PGI naught, means original, old value. So this value is 0 completely, so we are getting minus PGI naught, and you can see this value is written here. So this is the element, so we can have the storage of all the lines for ith units. So what we can do, let's suppose this is a vector, just we are considering this L, this it is equal to your here all the lines, and that is outage of any particular IS generation. So here we can, for I here, it is your, all the values are stored here, means line 1, 2, 3, 4, all the lines for IS. Similarly, if you are having another generator, so we are going to have another here column for this, so that we can have here L cross number of real power outage matrix. So all these factors are calculated and stored in the computer, and they are calculated on the base case, means we are assuming the same loading, but the loading can be changed. Once you are calculating, you are going to use that one, at that time the system loading will be different, but it is assumed that this will be giving, although some inaccurate, but this will be ranking the transmission lines outages cases, severity cases in the some reasonable accuracy. So here, as I said, we can calculate these factors at the base case, and we can store and we can use. Now we can see how we can use. These factors are pre-calculated at base case using the DC load flow relations, and are used to find the new line flows following the generator outage. Means here now the factors you are having. Now this value is outage with the some value. Here change in the Pi, you know this how much it is going to out, 1 unit, 2 unit, you can utilize this, and then with the old you can add, then you can get new line power flows. As then that can be used, because we require the Pi, we require the FL here divided by maximum value, that is known. So this value we know, and we can calculate from here. Similarly, let us consider a line K which is out, and it was flowing Fk naught an earlier case, and when it is going to out, what will happen? There will be change in other lines. What will be the value? So this was the K of line. So we are calculating power change in other line. So in that line, if it is out, it is 0, of course. So we are going to calculate the change in power flow. For example, let's suppose this line is out and this generator is active. What will happen? This whole 65 will be flowing here, and then it will be going 65 plus here it will be 100, here it will be going. This line is out. So this line power flow, the final value is 0. So what happens now? It is from initial it was 5, now it is 65. It is increased. So how much change? It is a 60, final minus initial. Similarly here we can calculate. So we can define the line outage distribution factor, means L denotes the lines where it is flowing, K is due to the outage. So we can change in L divided by Fk not here, and that's defined here. Similarly, we can again calculate these values, and then we can use these factors. Knowing these factors, with any change in the line power flow, we can get the new power flow, and then we can calculate the PI value and the performance index very clearly. So let us see using this distribution load flow, we can see some outages cases, and using PI how we can reformulate and we can recalculate and we can rank them contingency for again 3-bus system which I showed you here. Means I am talking about this system again. So here for this system intact, again you can consider the base case. Now I am going to consider this outage of one line. We are outage of generator first. Means once generator is going to out, what will happen? This value becomes 0. Because the P, if you remember, I found this P1, P2 and the Pn earlier it was 0.65. Now it is outage means 0. So we have put 0, and now we are calculating the delta 1 and delta 2. We are getting this value. With this, what we can calculate? Now we can calculate what will be the power. This is P1, 2 line flows. Now after outage of this generator, we are calculating. You can see in this diagram, again I can draw here even. This, it is here, and this is your load, and we are having another generator here, and this is generating power here, and this is here. Now if this is out, what will happen? This is generating now 100 megawatt power completely. This is your 100 megawatt. Whole the power will be flowing here to here. So this is 1, 2 and here 3. Means the power which is flowing from 3 to 1 will be equal to 1 to 2. Or it is 1 to 3 will be negative of 1, 2, and that we have written. 1, 2 will be minus 1, 3, that is this direction, because the power will be flowing here. And that we can calculate from this expression. It is at 29.4 megawatt. Similarly, the remaining power of 100, it will be going 70.6 here. So this is rerouted. And now what we can now form the PI. Again with the same real power flow performance index we are using, and we are using this WM value is unity. We are using exponent n is equal to n, means the square term. So we are dividing here 1/2. Now we are assuming the line rating. Already you can see the line ratings I have already explained here. The line rating of this line is 100 megawatt. This line is having 50. This megawatt is this line having 50 rating. Means it is 1 per unit, 0.5 per unit, 0.5 per unit again. So using this here, it is divided by, you can use the megawatt value or you can use per unit, of course no difference. So this divided by this square plus this divided by 50, this again minus value just we are taking, square 50, and you are getting 1.66 per unit. Now let us say for the line 1 outage. Line 1 outage means this line is tripped. Now this whole power will be flowing here, 100 megawatt, because the power will be not going. This will be coming 65 here and the 100 megawatt here. So again means we can see this line will be 100, this will be 65. In this case, even though there is no need to go for the delta calculation, sometimes you can see, for this is very simple system, but if you have a more interconnected system, you have to again form this matrix. This matrix is revised because this matrix is dependent on the line topology. So if line is going to be changed, line outage is going to be, then this matrix will be also changed. In the previous case, this network was intact, only generation was outage, only we change here. In this case, line outage here, we are this value is same, means we are going to take 0.65, here we are getting 1.0 with the negative sign, so it is not going to change. Now this is going to change, so we can again form that BF matrix, then we can go for the inversion, and then we'll find that we are getting this power, and then you can form this PI value, and you will get again with a similar here on 0 upon 100 because 0 power, and finally you are getting 2.85 per unit for this case for line 1 outage. Similarly, if we are going for the line 2 outage, if you calculate in line 2 outage, you will find this type of concept, because what is happening in this, you can see line 2 outage means we are going to out line this one 1.3, I think, yeah, 1.3 is going to out, yeah, this line is going to out. So what happens, this 65 will be flowing here and the remaining 35 will be flowing here. So in this case also there is no need to go for the farming again the B marks, we can simply see here using the simple Kirchhoff's law, and then using that we can just calculate and we'll find here these are the values 0.745. Again we are using the PI for outage this. Similarly for line outage 3 we can form and we'll see this value is this. Now you can see for the line, this line outage PI, this L1, it was your this value, you can see it was 2.85, it was 2.85, and this PI for G1 outage it was 1.66. Now you can say which one is severe. So that value which is giving highest, that is more severe. So this is our first severity. Thus we have ranked the contingency cases in the descending order of severity. Line 1 outage is most severe because this value is the highest, followed by generator 1 outage, this value, followed by line 2 outage, this value, then followed by line 3 outage, this value. So this is giving your relative order of severity for your outages, and that PI giving the real power flow performance index, and that can be used for your real power security analysis. So in this contingency selection just we have ranked all these 4 contingencies in this system. So line 1 outage is the most severe and line 3 outage is the least severe. The contingency analysis using the full load AC power flow will be carried out starting from the line 1 here outage and will stop when a contingency does not cause any violation. So now we can run the load flow, we can see whether this line flows limit are violating or the voltage limits are violating, then we can go for next, then we can go for next, and then we will stop when there is no violation, or even we can go for 1 or 2 more because there is some error in the calculation here, and then we can stop. So the online full load AC load flow is used for the only the critical contingencies, those are ranked in order of severities. Now let us see in the contingency selection algorithms what happens. You have ranked up to what level you have to go, that is basically the rank the PI based on the PI. So you have to have some cutoff mark somewhere, which PI just you have to go for. So if you are going for the PI, checking the PI which is means at what level, this is your ranking. So somewhere based on the ranking you have just taken this PI as a cutoff mark. In that cutoff mark there is a possibility if this value is higher, just you have checked this PI cutoff. So the PI which is more than this cutoff, that will be giving your critical contingencies, and then the PI which is less than that, we can say these are non-critical. We want to have some cutoff PI value so that we can say if it is more than that, system is critical, and if it is less than that, then that contingency is not critical. In that critical contingency here, those are ranked here the highest severity. This is a cutoff, this is a least. In that critical contingency there is a possibility that some contingencies are of course that are active, means they are critical, but maybe with some contingency maybe not critical because we are just making PI based on some approximate solution. So what is happening? So we can get some inactive contingency, some least without critical contingency, and we are getting some false alarm, means it is saying that this line is critical with the help of this PI, but actually it is not. So it is a false alarm that is giving. So this PI is a cutoff we have to decide, and again that based on the fast here the fast alarm, we can say this method is accurate or not. Now here just you can compare this cutoff, and you said this if it is less than PI, system is not critical, means not critical contingencies are there below this line. But There may be some inactive, no doubt. Contingencies below this, most of them will be non-critical, but some contingency may be critical. Some violation, some small error will be there. So, and that card is the misses. So this side we are getting some missing, this side we are getting some false alarm, and normally we have to define what is your false alarm rate, what is your capture rate, and that is defined with this here in this formulation. So the contingency selection algorithms are just in terms of their capture rate, that is a CR rate, and it is defined as CR is 1 minus NM divided by NC, here NC, means here this is saying NM is the number of misses out of this non-critical contingencies. As I said, here you are having 100 contingencies. Let's suppose 100 contingencies, and you have made some cutoff of 40, means PI which is more than that. Then here your 40s are your critical and 60 are you are saying is not critical. So in this non-critical contingencies, how many are the misses? How much are the critical contingency that giving you NM? Let's suppose 2 contingency here is your critical. It is said using your PI ranking, it is saying it is a not critical, but it is actually critical. So it is a 2, here NM is 2, here is a 60, so we can say 1 minus 2 upon 60. And that it is basically you can calculate what is your capture rate. Normally what we want this miss rate is 0, so the capture is unity. So the standard practice here, always we want the capture rate is unity and the false alarm rate should be 0. What is the false alarm rate? False alarm rate is defined as FR is equal to NFA, and that is defined as NFA is the number of false alarms out of NCC, means number of critical contingencies here, in this case 40. So if there is a suppose one false alarm is 1, so it is 1 upon 40 is your false alarm rate. We want this value should be 0, so it is a 0, means there should not be any false alarm. So our method we should choose, means always due to the inaccuracy in the model, it is the F CR is equal to 1, FR is equal to 0 is not possible. So we have to see the methods, various methods for that. So these are the basically false alarm rate and the capture rates, those are defined based on your the PI cutoff value. So always in the contingency selection, we have to go for monitoring what is your capture rate, what is your false alarm rate, and based on that we can say this method is giving very accurate result and it is decided. So just we saw the various methods for the contingency selections. Already I defined the contingency definition. Now once we have, as I said, we have ranked, then we can go for the contingency evaluation, where we actually check using your online AC load flow that whether there is any violation in the operating constraints or not, and then we can perform the contingency evaluation, and that consists of your complete contingency analysis part. In that contingency analysis part means that this contingency definition, contingency selection, then contingency evaluation, and that contingency analysis is not for either real power or reactive power voltage security analysis, but it is combined. We have to go for the real power security analysis as well as your voltage security analysis. So now I can just conclude, and then we'll give some more highlights that what are the next that we are going to have in this contingency security analysis. So online security assessment of power system requires it to decompose in the contingency selection and the contingency analysis of problems. Once again, this contingency selection and contingency analysis problem can be combined together if you are having very fast computational algorithm along with you are having fast computational platform. Then you can merge these two and you can go for all this contingency selections, means contingency definition lists. But we have some limitations, and therefore we go for contingency selection first, then we go for contingency analysis. Network sensitivity factors, that is the distribution factors, provides fast outage analysis required for the contingency selection. I listed several contingency selection algorithms, both including ranking and the screening methods. So this distribution factors are very fast. However, they are not used for high difference from the base case condition. If your base condition is changed too much, then these distribution factors will not give the accurate result. But here they are fast because this one inverse is required for all this analysis. These are well established for the line security evaluation. Recent work has shown feasibility of such factors for the voltage security as well. Earlier, these distribution factors were very widely used for the line security analysis, or you can say megawatt security evaluation, but nowadays they are also used for the voltage security evaluation. I did not discuss how these distribution factors methods are basically that we are going for the voltage security evaluation, because there are so many distribution factor methods are proposed in the literature. So it is not possible to do that, but you should know that these distribution factors are very widely used for both line as well as your voltage security evaluation purposes. Nowadays, another recent requirement that we should go for the static security assessment. So far I was discussing that the static security analysis. Now the people are talking about the dynamic security assessment as well, which will require the incorporating the angle stability and the voltage stability constraints in the line and voltage security evaluation respectively. What is that? What we are going to do here in this dynamic security, we are doing nothing here. The same this static security analysis, plus we are adding some, that is your voltage and your angle stability here. Problems means we are using some dynamics of the system, means here voltage and the angle stability are added, and then if you are going for this, then it is called your dynamic security. So this is very demanding, means it is very challenging. Here we require very fast computation. You know, the solving the dynamics of the power system requires a lot of time. So we have to take care very carefully, means we have to use very fast methods for this dynamic security as well. But so far, although there are so many researches and papers are available for the dynamic security as well, but here this has so many problems again to solve the power system dynamics along with the static security limits and operating constraints. The system, if you are operating in the dynamically secure system, it is very, very expensive. Means we have to see that if one line is out, now the fault duration at the dynamics again, then you can see whether your system is stable or not. So in this module here only I took the 2 lectures, already it is proposed for 4 lectures, but the sum of the part already I explained in the module first, where about the security monitoring importance, security optimization, etc. But here in this contingency analysis, just we saw, first we saw the various operational and control hierarchy, then we also went for this some restorative emergency control actions, and then in contingency analysis I described completely your contingency evaluation, contingency selection, and your contingency analysis, means evaluation you can say. So this analysis part is your definition, selection, and then it is your evaluation. So these 3 parts basically combines your security analysis, that is analysis, or sometimes it is called contingency analysis or security analysis, both are the same term. And if you are going to include the power system dynamics along with the voltage stability limits and the angle stability limits along with your static security limits, then we can achieve here the dynamic security, and that is again can be a further research topic. A lot of research already people are doing, but still we require very fast and accurate method for this, because in the power system, the now if you are including, as I said, there are thousands contingencies, more than that 1,000 contingencies are existing. Now you are going to include the contingencies with the its critical clearing time, how much it is, which type of faults, you can assume how many faults are there in one line. So it is again number of holes set is enormous, and then we are going for this again contingency selection and analysis. For dynamic security, it is very, very hard task. So we require very fast, we require some sort of here fast calculation of these, and so that we can go for the dynamic security analysis or assessment as well.